Hello, welcome back to another video. And yes, it has been quite some time since I have uploaded a video. And yep, I'm right now. Well, the last time I uploaded a video, I was in my first year of my undergraduate. Now I'm in the third year of college, and I thought, hey, why the hell not? So I have taken some time out, and I'm planning to start making videos again. And let's see how it goes. Hopefully, I still have time in between all my other work to do some stuff. So, well, yeah. Now, okay, now about this video. So, what I'm going to do in this video. So, this video, I'm going to be talking about the Monty Hall problem, a pretty straightforward problem. If you are interested in probability, you must have seen this in tons of videos before with different interpretations of how to solve it, and and just different ideas. And so, I'm just going to show my interpretation on how I solved it and different variations of that problem itself. So let's go into it. Okay, so the problem is pretty simple. The problem originated from the game show Let's Make a Deal, which is hosted by Monty Hall, which is how the problem got its name. Now, the rule of the game is pretty simple. You're given 3 doors, behind 2 of which are a goat. There are 2 doors, behind each is a goat, and behind the third door is a car. Now, you are given a choice to choose any of the 3 doors. Now, let's you choose door number 1. Now, you don't open it. The game show host opens one door out of the other 2, which contains a goat, and opens it. Now, you're given a choice. You can either open the door which you had initially chosen, or you could switch and choose the door not opened. And now, probabilistically, is it in your advantage to switch or to maintain your choice? Now, that is the question. Now, initially, the assumption is that, okay, now since the door which has the goat has been opened, now you're left with 2 doors, one which has a car and one which has a goat. So the probability should be 1 by 2 of winning either way, right? Now, but the thing is that if you look at it mathematically, it doesn't seem to hold. And that's where I come in. So we're going to look at it mathematically and see why it does not hold. Okay, so let's look into it mathematically. And now we have someone threatening me with Monty Hall. Okay, let's just ignore that, I guess. Okay, so now we have 3 doors. And for some reason, my writing pad is going pretty slow. That is disturbing, but something we'll have to deal with, I guess. Okay, so now this is door number 1, door number 2, door number 3. Okay, now let's just see, without any switching element, what is the probability of us winning a car. So there is 1 car and 2 goats, or let me just say goats, and this is 1 car. Okay, so probability of winning a car is 1 by 1 plus 2, which is pretty simply 1 by 3, the probability of winning a car behind either of these doors. Okay, right, that's pretty simple, right? Okay, now, so this just shows that it's equally distributed. Now let's just say that the game shows randomly says, okay, behind door number 2 there is no car. And like let's just assume that we had initially chosen 1. Right, so we had initially chosen 1, then the game show host says, okay, behind 2 there is a goat. So now, what is the probability that there would be a car behind door 1 and the probability that there would be a car behind door 3? Well, now let's look at it systematically. Would there even need to be a change? Because right now all we have is that there are 2 doors and we have 1 car and 1 goat. So the probability of a car should now just be 1 divided by 1 plus 1. 1 car and one goat. So probability of car behind either of the gate is basically 1 divided by 1 plus 1, which is equal to 1 by 2. Is that really correct? Well, no, not really. Because because like right now all we have are the initial probabilities of each element. Let's just say element, and element being a car or a goat. So the initial probability of a car being behind any of the door is 1 by 3, and the probability of a goat being behind is 2 by 3. Right now all we have are these probabilities. So now our main goal right now is to convert our new problem statement after removing the door number 2 into one of the initial conditions, right? Okay, so I'm just gonna erase this because I really like this diagram. Somehow it has come out pretty nicely. Okay, so now what is the probability that we get a car given that we switch? Well, I'm pretty sure I spelled it wrong, but given that we switch, well, there you go. I'm just going to actually just move this out. Okay, now so let's see what is the probability that we get a car given that we switch. So we have chosen door 1, and the probability of getting a car if we switch is the probability that the car belongs to gate number 3, right? Because that is the only available option to us, and if you want a car, we need to have that the car belongs to gate number 3. And that also means that gate number 1 has a goat, right? So basically the probability that we get a car after switching is the probability that our initial guess was that of a goat, which basically is this, which is 2 by 3. And the thing is, the probability that we get a car given that we don't switch would still be the probability that we get a car, okay, behind gate 1, which is basically 1 by 3. So the odds are not in our favor if we don't switch, but if we switch, then we get more than a 50% chance that we would get a car. And forget the 50%, it is definitely more, there is a higher probability of us getting a car if we switch than if we don't switch, which surprisingly is different than our initial 50% probability which we had thought of initially. Now this comes up with a lot of variations. So now the other variation of how people explain this problem, explain the solution, is that once we have chosen this gate, this probability remains the same, and once we cancel out this door, that behind this door there is no car, then this probability shifts to door number 3, which is stupid. Like, that has absolutely no intuition, and it doesn't make any sense. Like, why would that even work? Like, that is just a weird way of telling a fairy tale to someone. That is how a lot of people explain the solution to this problem. There are more methods like the more mathematically inclined approaches, like using Bayes theorem, which I will get to. Okay, so the simple idea behind the Bayesian method is, okay, let me just give a brief reminder or recall of what the Bayes theorem is. And I have done a video on proving Bayes theorem, which should be on the top right. So the Bayes theorem is basically just says that we have two events A and B, and the probability of B occurring given A is basically probability of A and B given and divided by probability of A, or you could just call this A intersection B, same thing really. Okay, so now, and also it can also be interpreted as probability of A into probability of B given A is equal to probability of B into probability of A given B. Okay, so that's the Bayes theorem. Okay, so right now over here, okay, yeah. So right now we're taking two events. One is the probability that there is a car in one of the other doors, in other door, and B is the probability that there exists a goat in the door, in one of the doors not selected. I'm just gonna call it one off. Okay, now let's just get some basic things out of the way. So the probability of A is 2 by 3. Am I right? Yeah. So probability of A is 2 by 3. Because we have the what's the complement of A? That is that there is a car in the door we have chosen, in the chosen door, and probability of that is basically equal to 1 by 3, which we've already discussed. And since these two sum up to 1, so this is 1 minus 1 by 3, which is 2 by 3. And now probability of B given A is equal to 1. Like I mentioned before, there is always going to be a goat in one of the other, in any of the two doors we select, because there is only one car. So in either of these events, there is definitely going to be one door behind which there exists a goat. So that is one. Okay, so what do we care about? We care about the probability of A given that there is a goat behind one of the other doors, right? Because that is what has been done. We have chosen a door and we want to see what's the probability of getting a car if we switch, or if there is a car behind the other door, and we are given that there is a goat behind one of the other two doors, right? So that is basically probability of A intersection B divided by probability of B. Or we can basically just write this as probability of A given B, no, yeah, my bad. A give, or what am I doing? Yeah, probability of B given A into probability of A divided by probability of B given A into probability of A plus probability of B given A complement into probability of A complement. Now this is basically just by the law of total probability, because this is basically probability of B and A plus probability of B and A complement. So probability of B intersection A plus probability of B intersection A complement. Since these both are completely disjoint sets, we can take the union of both these sets and find the total probability, which is basically equal to probability of B. Oh, my bad. That is only true because the probability of A and probability of A complement is equal to 1. If we take a subset of A complement or subset of A and we try to do this, that won't work. So we need the probability of A and A complement to sum up to 1, which it does. So this is basically a law of complete probability, which I will probably make a video about later, but right now I don't have a video about it. Or you could just search it up, law of total probability. That is the law which I'm talking about. Anyway, so now what is the probability of B given A, which I have mentioned is 1. Probability of A is 2 by 3 divided by 1 into 2 by 3 plus 1 into 1 by 3, which turns out to be 2 by 3, which was basically the probability which we got before. That if we switch, there is a 2/3 probability of us getting a car on the other door. So switching generally works well. Well, so that's it for this video, and yes, I do have a whiteboard, and you might be wondering why I don't use a whiteboard to make my videos. Well, that is mainly because the lighting is not very good, my whiteboard is not very big, so anything I do over here, it might not be very clear. So to make my videos good, I use a writing pad and not my whiteboard, because lighting and small size. Well, I hope you enjoyed this video, and please like, share, subscribe, comment on my channel and videos, and it would definitely be really awesome. Thank you.